So we said, okay, so we said for all the folks who have been given the remdesivir drug, 541 folks who have been given the remdesivir drug, they took the median time to recover, and that median value is 10 days, and the 95% confidence interval of that median is 9 to 11 days. Now we will continue where we left off and discuss how all these can be computed. But before we go there, let's quickly go to this research paper again. Quickly go through it. Okay, the key point that I wanted to compare, we have it anyway. So they compare again, since this is a rigorous research paper funded by National Institute of Allergy and Infectious Diseases, tons of actual trials done, fairly serious work. So they don't just use one metric. Very often, a lot of researchers use multiple metrics. But the key metric here is the median recovery time, which they use as a primary metric. And instead of just using a point estimate that the median recovery time is 10 days, they're also looking at 95% confidence intervals. Similarly, they have multiple other tests that they report here. One very popular test is called the Kaplan-Meier estimates, which is a part of healthcare statistics. And this is used in healthcare and other areas where you have to look at how long does somebody survive. Okay, so this is as far as mortality. So when they compared mortality using Kaplan-Meier estimates, again, there are a bunch of estimates that are very, very widely used in medicine. For our discussion, we'll focus primarily on confidence intervals and median recovery time. We'll discuss this. There are a lot of other tests also that they perform, because, I mean, come on, this is a serious final report of remdesivir. It's not a joke. So people are looking for multiple real world signals that this is useful. Okay. So again, the key point here is, while the paper itself says very clearly that the primary outcome was time to recovery, this is the primary one, but they also have other metrics that they computed. They also say how much drug was given, like 200 mg loading dose followed by 100 mg for 9 additional days. They give you all the medical details here. Okay, so in real world medical research, it's not just one metric. Oftentimes there are multiple metrics for that. This is about infectious diseases, so they look at, especially for like severe infections in COVID, they look at mortality rates, some estimates, some tests accordingly. So we'll limit ourselves to this because we're not going into healthcare statistics per se. Cool. Again, the conclusion of this research paper is that remdesivir, okay, so where is that conclusion? They've written it here. Our data shows that remdesivir was superior to placebo in shortening the time to recovery in adults who are hospitalized and have evidence of lower respiratory tract infection. And this work is funded by National Institute of Allergy and Infectious Diseases, etc., etc. Right? So this is the conclusion, while there is all these results that have been published here. Okay, so in medicine, okay, so let me just go here. Okay, let me see if I can zoom into the paper. There are some parts of the paper I wanted to zoom in. Okay, so there are all these plots. Again, I would okay, so I would want you to go through this, okay, if time permits. Maybe not now. I'll provide the link to this in the notes. There are 1,114 patients who are assessed for eligibility. Some people were excluded for various reasons. Maybe they have some disease, or they have some condition. Maybe somebody was pregnant and they could not administer remdesivir, or somebody was more than 80 years old and things like that. So only 1062 people underwent randomization, of which 541 received remdesivir, 10 did not for whatever reason. Probably they didn't come to the hospital to pick it up. So 517 received placebo, and number of doses. So they talk about everything that has happened there. This is all the data. This is how they actually conducted the A/B test. So it's very informative to read this, because in a real world test, people stop coming. For example, 10 people did not receive remdesivir because they said, no, I don't want these experimental drugs on me. While they initially signed up, probably they changed their mind. Okay, so this is very important to understand. In the real world, things go crazy. So experiments you have to be very careful of when you're doing in a medical setting. And thankfully, the governments have very strict guidelines. Now here comes the fun part. This is what I really love. Okay, let me explain what these are. Okay, so on this axis, 1 basically means that neither placebo nor remdesivir are better. 1 basically means, relatively speaking, again, that's what this measure is. This is basically recovery rate ratio. This is the ratio of recoveries of remdesivir patients and non-remdesivir or placebo patients, right? One basically means that there is no difference between placebo, which is basically giving no medicine, versus remdesivir. So as more and more data is on the right side of this, the more right side, the better remdesivir is. The more left side, the better placebo is. Obviously, how can placebo be better realistically? So here are some, again, they do a lot of rigorous analysis on this, and this is the fun part in medicine, at least one of the fun parts. So across all the 1062 patients, they realized that, again, this is 1, right? This value was 1. Anything on this side plus remdesivir is better. Anything on this side, placebo is better. Okay. So if you see, this is the point estimate of the recovery ratio. This is just the point estimate. But if I just showed you the point estimate, I'm not getting, again, in any plot like this, what they're trying to show is this. Okay, let me show you what this plot means. So in all of these medical plots, you're shown something like this. This middle value, let's take our example itself, right? The median time to recover. Okay, so the median time to recover is 10 across all patients, across all 1062 patients. Sorry, not all 1062, I'm sorry. All of the 541 patients, I'm sorry. 541 patients that got remdesivir, median is 10, but the 95% confidence interval is between 9 to 11. This is how it is depicted visually. So one thing that you have to understand here is the wider this is. Okay, let's take people who got placebo, right? 521 people, if I'm not wrong. Yeah, and their range is 13 to 18. Is that right? 1 second. Something seems fishy. Just a second. How can 13 to 18 be there and 18 is the median? Let me see this. 15 is the median. Okay, and 13 to 18 is the interval. So I probably miswrote it. Okay, or I wrote it incorrectly or misquoted it. Okay, so with that out of the way, so for the placebo, their median value is 13. So 13 will be greater than this, and their range is, what is the range? I keep for so 13 to 18. Sorry. So 13 to 18, and their median value is 15. So if you see both these intervals, one key takeaway for you is this: that again, this is the range of the median recovery time. Okay, this is the range of median recovery. So the median recovery time, if you think of this as a random variable, 95% chances it will lie in this range. 95% chances for the placebo people it will lie in this, which means, again, we want people to recover faster, right? Which means your remdesivir is significantly better than this in most cases. In most cases, it is significantly better. That's the key idea here. So in this diagram, okay, so let's go here. In this diagram, instead of median time, they've given some recovery ratio. So if you see this, what this is telling you is very interesting. Look at this. What this is telling you is the median is okay, but the 95% confidence interval is quite wide because there are also some values on this side. Similarly, if you take this, okay, so this is Asians. Asians are typically people from Southeast Asia, China, Singapore, etc. Right? So on Asians, when remdesivir was tried out, their median value was 1.07. Remember, 1 basically means that the placebo and remdesivir are one and the same. But the 95%, again, this is just over 1. But the 95% confidence interval is quite wide. So if you see this, the remdesivir is working significantly better for white people and also for black people than Asian community. It's also working well for other communities like Polynesians and other races, right? So this is very important. Again, one key takeaway is probably because of the genetics of Asian people, Chinese, Singaporeans, Malay, etc. Probably this remdesivir is not working as well as compared to white or black or even Hispanic people to a large Hispanic or the Mexican Americans, etc. Right? So this is very important. So we are no more looking at 1 point estimate. We are looking at the 95% confidence intervals. So a lot of modern medicine is slowly moving into the world of 95% confidence intervals. This is a process that started long back. We'll see how to compute the 95% confidence intervals. But the question here is, why has healthcare moved to confidence intervals? Why are they not doing statistical tests? It's not that they're not doing statistical tests. Even in this remdesivir study, they're doing some statistical tests. But their key value that they're looking at is a confidence interval of the median. And the reason for it is the intervals are better than point estimates. Okay, we'll see how to compute this confidence interval in a couple of minutes. A point estimate basically says, hey, the median is 10. But what if the median is 10, but the 95% confidence interval is very large? Then what happens? Again, this 95% confidence interval tells me something about the distribution of data. For example, if somebody tells me that the median is 10, the 95% values lie between 8 and 32. Somebody says this. Then I know, boss, this distribution is like this. Right? While the median value is 10, there are a lot of people who might take more than 30 days also. So by just giving the 95% confidence interval, I can get a sense of how wide this distribution is. There is a 95% chance that my median will lie in this range. Okay, so point estimates, not very powerful. Intervals and hence distributions are very powerful. Even in A/B tests in large companies, at least in the organizations that I worked at, imagine if you have this setup, right? Very simple setup. Imagine if I have, okay, let's take this example of Netflix itself, right? Suppose I have some A, some thumbnail, and I have a thumbnail B. Suppose I showed it to a bunch of people. Okay, I showed this to a bunch of people. And then I computed the CTR, the click-through rate. I computed the CTR. Now, the CTR that I'm computing is just one number. I don't want to compare one number. I want to get a 95% confidence interval. So confidence intervals are a much better strategy. In some instances, especially in healthcare instances, also in other instances, confidence intervals are a great strategy to compare controls and treatments, or to control, or to say, hey, does placebo work better or remdesivir work better? Now, given that context, the big question here is, how do we now compute these confidence intervals? How to compute confidence interval? Okay, so there are many strategies of computing confidence intervals. I will describe one strategy which is extremely powerful, very widely used, called the bootstrapping technique. Bootstrapping is a much more general strategy in statistics itself, in computational statistics, but very widely used in computing confidence intervals. So let's take up a problem. I'll just write the problem clearly for you. Okay. Suppose imagine I have remdesivir versus placebo. The number of days it has taken for people to recover. Okay. So remdesivir 1, remdesivir 2. Suppose I have some 500 people here. I'm just making some numbers up. This is placebo 1, placebo 2, some placebo 500 people. I'm just making up. Okay. So these are numbers. These are number of days it has taken for people to recover. Okay. So very simple. Now, if I compute a median of this, again, what is our metric that we are looking for? Median recovery time. Okay, so let's take that example itself. Now, if I compute the median of all these numbers, I'm going to get only one value, right? I'm going to get, let's say, one median of R over all 500 values. If I compute the median of all these, I will get the median of all placebo across the 500 people. I'm just going to get one point estimate. If I take the median, this point estimate was, we saw this a while ago, right? So this point estimate was 10 and this was 15. Okay, so this point estimate was 10, this point estimate was 15. Now, how do I get the 95% confidence interval? I remember the only data that I have at my disposal are these 500 observations and these 500 observations. I don't have any other data. I still want to get these 95% confidence intervals. That's where the beauty of bootstrapping is. Okay, so let me explain how bootstrapping works. Let's look at the remdesivir folks, right? So let's look at all the folks who have remdesivir. Let's understand the strategy of bootstrapping. So you have remdesivir people, R1, R2, so on and so forth, R500. These are 500 real observations that we have. From these observations, we'll do two things. Okay, so the first thing that we will do is this. I will randomly sample values from this with replacement. Okay, so this is sampling with replacement. Sampling with replacement. Now, what is sampling with replacement mean? Let me explain that. Sampling with replacement means, okay, so I will construct a sample now. Okay, let's call this sample S1. How will I construct this sample? I will randomly pick one of these values. So let's assume I pick R2 and place it here. Because I picked R2, it doesn't mean that I will remove R2 from here. I'm not, sorry. So I'm not going to remove or replace R2. I'm going to keep R2 here. I'm going to again sample. When I sample again, I might get R123. I will randomly sample from this. And this sample itself, I will sample 500 values with replacement. Okay. So which means I will, again, I could, after, when I sample these 500 times, I could again get R2 in one of the samples. That's possible. Again, remember, in the whole concept of bootstrapping, what is the only data that we have? The only data that we have, this is the catch. The only data that we have, where did that, okay. The only data that we have is this. We don't have any more data. From this data itself, I need to get confidence interval. So I will behave as if this data is the whole universe or the whole population. Actually, what I have is not the whole population. What I have is a sample of 500 observations. But since I don't have anything else, right, this is all I have. What I have is actually a random sample of size 500. But this is all I have. I have to live with this. Given that I only have a random sample of 500 and I have to live with this, assuming that these 500 values are truly random, I will treat these 500 values as population. That's what I've done. I will treat these 500 values as population and I'll keep sampling from this with replacement. Right? I'll keep, so R2 can occur multiple times. So I got my sample 1 now. So now we are not yet done. So when I got my sample 1, I will compute the median of these 500 values. Remember, this is very important. When I'm sampling like this in bootstrapping, same value can occur multiple times. That's okay, no problem. The probability of that happening is low, but it does happen. Okay, so on my sample 1, bootstrapping is basically sampling with replacement. So when I do this, I will get median 1. We are not done. So again, I will do that. I will again do bootstrap sample. These are called bootstrap samples. Okay, assuming that this is my population or this is a good representation of my population, I'll again sample S2. Again, I'll get another sample. 500 times I'll keep sampling. Okay, from that sample, again, I'll compute M2. I'll repeat that again. I'll get sample 3. From that, I will get median 3. Right? So if you think about it, from my original R1 to R500, this is my original data that I have. This is the original data that we have. Using this data, what are we doing here? We computed S1 and we took the median M1. So we took sample S2. These are bootstrap samples. Okay? These are bootstrap samples. Right? These are bootstrap samples, right? This we have M2. Again, we do S3. This is just computational exercise, right? We can keep repeating it, right? I'll keep doing it some K times and I get MK. Now, here is the fun part. Now I have these 500 values. From these 500 values, I computed a median. That median that I observed was 10. I think it was 10, right? I keep forgetting this. Yeah, it is 10. So the median that I observed here is 10. But now to get the 95% confidence interval, I take all these values. I sort these values. Let's sort them. Let's sort all MIs. All these MIs, all these MIs, all these medians, I will sort them. When I sort them, I'll say, hey, give me the middle 95% values. Again, let's assume I sort all of them. There will be some let's say 2.5% values here, greater than this. 2.5% of values will be greater than this. So what will I have here? This will be my 9. This will be my 11. And this is anyway 10. This I got it from the original sample itself. K is basically any number I choose. Typically, we choose K to be a reasonably large number like 1,000. Again, this is very similar to permutation sampling, like permutation testing. In permutation testing, we created a bunch of samples, right? We did the shuffling and sampling over and over again. Here also, we are doing bootstrap sampling. Very simple idea, right? Now, the moment I get these K medians, again, there is typically, again, good question. So the question here is, how do you pick the right K? Typically, if you pick K to be close to 1,000 or 10,000, it's fairly reasonable. Okay, 1000 to 10,000 is what people typically use. And again, even if you change K beyond 10,000, this confidence interval itself might not change significantly. It might change slightly. So this is the idea. Again, look at the power of this. If you think carefully, right, with bootstrap sample, right, with bootstrapping, I'm computing a 95% confidence interval on the median recovery time, and all I have is just 500 observations, nothing more. All I have are these R1 to R500. Again, bootstrapping is a terrific strategy. It's used quite extensively in machine learning also, right? It's used very, very extensively. Now, it works phenomenally well in practice. Okay. So again, remember that what we are computing is a 95% confidence interval on the median. Now, somebody is saying, why can't we use central limit theorem? Oh, there's a glitch there. What does the central limit theorem say? You can't use central limit theorem everywhere. Is that the mean of a random variable. So suppose you have these observations, right? The mean of this is Gaussian distributed. The mean is normally distributed. It doesn't say anything about median. You can't use central limit theorem for everything. You can't use it especially for things like medians. Okay, so central limit theorem is applicable mostly for simpler metrics like means. While bootstrap sample, instead of median, I can compute anything, right? Look at this. Just like the way I computed medians here, I computed median here, right? I can compute it for anything that I want. Again, just like your permutation testing and Mann-Whitney U, bootstrapping is a non-parametric strategy. It is completely non-parametric. I'm making no assumptions about the distributions, and I can compute confidence intervals for anything like this, right? Again, very, very important strategies that you have to think of. So CLT is not used much in this because of the underlying assumptions and things that random variables have to satisfy. And it only works for things like means and sum and things like that. It won't work for medians, right? So bootstrap sampling is a very, very simple, very, very powerful. It takes 10 minutes to write this code. Look at this. What are you doing here? It's actually very, very simple. Okay, you have these 500 observations. You've taken different samples, S1, S2, S3. You're computing their medians, and you're just getting a 95%. You're saying, hey, in which interval 95% of values lie? It's just sorting. That's all. You just sort it, and you say, hey, between 9 and 11, 95% of my values are there. 2.5% of values are less than 9. 2.5% of values are greater than 11. That's it. You just find this middle value and you're done. You got your confidence interval, right? And this is super duper powerful. Again, the first time I learned about this, I said, hey, are you joking? Does this even work? Yes, boss, it works phenomenally well in practice. Okay. So the next question here is very interesting, which is what should be this size? What should be the size of my sample, right? Because you want to compute the confidence interval on the median with 500 observations. Again, you got the 10 value that you got, right, was the median of these 500 observations. So the median recovery time, this is the random variable, right? The median recovery time, you want to get a 95% confidence interval with this value as 10, this value as 9 and 11. You want to get the interval of the median recovery time, assuming that there are 500 patients using which you are computing the median. That's why in each sample, we are creating a sample size of 500, right? So that's the core idea. That's the core simple idea behind this. Okay. Okay, very simple, right? Very easy also to understand. And nowadays, so you can think of confidence intervals as a very, very good strategy or an alternative just to doing A/B tests. And again, how do you conclude from this that something is good or bad? Very simple. You take this, right? This is remdesivir data. This is placebo data. Now, these two intervals are not overlapping. These two 95% confidence intervals are quite far away from each other, actually, right? And that's good, which means that, again, we want lower values, right? We want people to recover faster. And if there is a 95% chance that the median recovery time of those who have taken remdesivir falls in this interval, and this interval is not overlapping with this, right? This interval is significantly larger than this. We can say on an average, people who have taken remdesivir tend to recover significantly better than people who have not taken remdesivir. Right? That's the idea here. Okay. Now, the median. So another question here is, what will be the median of? Oh, sorry, my bad. So what will be the median of? Where is this? Where is that slide? Okay. So what will be the median of all these values? The median of all these values. So you're taking a median of medians. Most likely, it will be very close to 10, if not exactly equal to 10. It will be very close to 10, right? So this is how you compute confidence intervals, and confidence intervals are a very valid alternative to just doing high. Again, even in confidence intervals, you're doing A/B testing, but instead of using statistical hypothesis testing, confidence interval is another very useful strategy. But in a lot of real world, what people do is they do hypothesis testing, they get the p-values and all of that, and they also look at the confidence intervals. It's like two pieces of information through which they will say that yes, the confidence interval is good enough, or they can look at this sort of data and say for Asians, not this is the Asians. So for Asians, remdesivir is not working very well, so we may not as well give it or ship remdesivir to China or Singapore because it's not working very well for these people, right? So